Sempre sono okay. One more minute. Subito. Sì. So it's a great pleasure to introduce the next speaker, Pavlo Gavrylenko from SISSA, I guess. We speak about Isomonodromic deformation on a torus, Fredholm determinant, and connecting contracts. Thank you very much.
Thank you very much for inviting me to my conference. It's my second time here. So I talked about some papers which are also duly ordinary under some condition. I tell about some of the updates Fabrizio the Monte we share with the year. Here's the plan. First, I'll tell about the equations we have studied. So basically, it is this equation. So it is just a particle moving in the potential given by the various cost function. And also on the time in this problem is the modular parameter of the torus. So it is an autonomous system. And if you want to take autonomous limit, it is possible. We should say that this coefficient in front of the potential becomes very big. Energy should also behave in some appropriate way. And if we do this, so energy should basically stay like 1 over squared. And then if you consider evolution in a fast time, then this becomes just a usual coordinate modular system for the particles. A particle moving in this potential. Let me tell this because it is usually useful to compare phenomena which happen in the non-autonomous case to phenomena which happen in autonomous case, and also to study the limit n equals to 0 when this particle becomes free. So what can we say about these equations? So if you talk about autonomous equation, then it is a system with two-dimensional phase space, and there is one Hamiltonian. So it can be integrated explicitly. If you look at the non-autonomous one, and want to study Sylvian compatibility, so formally introduce another variable, Hamiltonian. The time it becomes something four-dimensional, still with a single integral of motion. So namely, it's not a Liouville. But nevertheless, it turns out that the solution of the system can still be a ring. Actually, that equation on the first slide was some variant of Fenova 6 equation written in the elliptic form. And as you know from the paper by Desiraju, we can write the solution of the Fenova equation explicitly. The only peculiarity here is that it is written in different parameterization and it uses different to write this explicit formulas. So this problem is on a torus, that problem is on a sphere, and it's just a coincidence for puncture sphere and considered with one puncture torus. In general, they are representatives of different families of Isomonodromic problems. So, about this explicit formulas. So to solve autonomous system, the solution looks this way. And we have a curve with the parameter tau 0. This tau 0 is a period of the underlying curves. We have some covering spectral curve given by the equation K squared equals to energy plus m squared times VF. And it has the antisymmetric differential, antisymmetric ambiguous involution, and its period is some tau, I call it tau Gavrylenko. So, and the solution is written like this. This ratio of tau functions of theta functions of coordinates equals the ratio of theta functions with a different period, depending on some point on a torus, which shows linear. If you solve this equation for Q of t, then it's a solution of autonomous collaterals. And if try to generalize this formula to the non-autonomous case, then it looks like this. On the left-hand side is the same. We need to solve the same equation in elliptic functions, but the right-hand side is modified. It is somehow similar to the theta function, and it also has a limit and goes to 0 and shows into the actual theta function. But in general, it contains some objects. Like this one is just a product of both functions, which are arrived later. This is from the theta function. And this one is a conformal block on torus with one function or partition function of n equals to 2 star gauge theory. This does not matter because on this subject just has some explicit expression which I will write, and it can be obtained without CFT or gauge theories. It can be obtained in its combinatorial way. That's all. Well, the formula of this C is here. So here the definition of conformal block on a torus is just trace of some operator with the appropriate weight. So here the definition of this function b, which is a conformal block or a partition function, which participated in that formula. So it is some prefactor times sum over a pair of Young diagrams, and the expression under the sum is the ratio of products of some elementary building blocks, which I denote by because they particularly in Newcastle studies of this partition functions. So this letter n is some function of two Young diagrams and of complex number. And it is given by product over the boxes in one Young diagram, product over boxes of another Young diagram, and once in this product. X shifted by so-called arm lengths of a box and lengths on a box. So this arm and lengths are defined with respect to some Young diagram, and they are functions of a box, arbitrary box in place. They are also defined for boxes right here. They don't become negative. So there are these natural expressions, and they give a specific formula for this conformal block. The first two terms have this form. And one check that we can do here is to put m equals to 0 and see that it turns into this order. Basically, to dedicate the one q plus 2 square. But in general, it is some function. And also, if you want to look at the even behavior of this formula, again, in this almost trivial case, when m equals to 0, we can just see that the conformal block becomes this function which we saw structure constants become trivial. So these expressions sum into the theta functions, actually even simple theta functions of the same models. So in this way, we can recover the free particle evolution, which it should be for n equals to 0. And it depends on two parameters. One is zeta, initial coordinate, and some a initial moment. Are there any questions? So now there is a question: how to get such a kind of explicit solutions to this problem? And to do this, zero in the integrable systems, it is good to switch to appropriate linear problems that correspond to this system. So if it is autonomous collateral, then it has this well-known Lux pair with the Lux matrix that has a single pole at 0, and no singularities in the other points. There is also this matrix that describes evolution. So there is this Lux evolution given by the usual formula. It tells that Lux will be transformed by some conjugation. So it's it's this ratio of theta functions. Yes, so it's not okay. So this X has a first order pole 0. 0 somewhere else, and because there are only two such points, it has a non-trivial phase when we continue along the B cycle. Okay. And it's periodic when we go direction A cycle. So there are two different Lux factors with collateral model. One is due to Taksaki, another was written by Korokin, maybe the authors. So this one is such as Lux flux pair. And in this case, we have some parameter in the modular properties of the flux matrix itself. In the concordance flux, there is no continuous parameters, and they're transformed by conjugation by some sigma matrices. Has no parallel, bottom parallel also, and limited by some modification of bundle, which I don't remember exactly how it looks like. It's called only Kekka transformation. Okay, so here are the transformation properties of this LX. So when there are no functions with a singularity as 0. So we should get something on table when we continue on the at least one step. So there is this transformation property, which tells us that this Lux matrix acts not in a parallel vector bundle as was in the spherical problems, but on some vector bundle on a torus. And this Q, which is coordinated particle, is a modulus of this. And the autonomous problem also has this Lux type description, but it is now Isomonodromic Lux, because the first equation now is the linear system. dz of y should equal to y times L. And the second equation is the same. Because of this derivative, now this consistency condition contains not only the commutator but also this z derivative. And so now the spectrum of the flux is not. In this case, have another set of quantities which look much more like initial data, not as integral motion. In this case, we have a monodromy of solution of this linear system being invariant under this evolution. And monodromies are defined a little bit trickier than in the spherical case, because this solution is a section of an integral bundle. So when we continue on the A cycle, it is just multiplied by monodromy on the left. We get an optimization of solutions instead of original solutions. And when we go along the B cycle, we should also multiply by this diagonal matrix on the just the our bundle is not trivial. And this modular matrices are parameterized by the letters which appear in the formulas for explicit solution, which is also called a Kyiv formula, because all those are from Kyiv. So parameterization is this one. A is the eigenvalue of MA, and eta is some number which is responsible for transformation when we take a matrix MB and multiply on the left by some matrix MA to some power. So it is a kind of parameter of a continuous geodesic parameter of a geodesic flow and related to the A side. So there are complex variants of continuation coordinates. And if you look at the frame particle case, then they are coordinate and the momentum of a particle. So and so this also this mass cancels and this matrix maybe becomes also there, you know. Yeah. Which was formula So this theta and A are here. So now we have this linear system, and the solution is first some complicated function, which is even more complicated than the tau function. At least it is some matrix. First, suppose that you want to find some approximate description of this solution. It can be done using some techniques similar to what people use in the problems of the sphere. Namely, we can try to approximate solution of this linear system on a torus by something that can be computed. Namely, by a solution of a system on a sphere with three functions. So we adjust the monodromies of this three-point problem in such a way that monodromy around zero around the singularity and monodromies around the two neighboring cycles, this one and this one, coincide. So this monodromy is MA, this monodromy is MA inverse, conjugated by MB. So we take a linear system with these three functions, which are here plus and minus infinity and zero. And saying that there is some solution of this linear problem, which is written explicitly in terms of trigonometric. And we consider the ratio of two such solutions. And the main effect of this division by three-point solution is that, and now we get some function that is analytic in one fundamental domain of this torus. So if I draw this in the same picture in a different way, namely if I draw it on a plane, it looks like this. So our original torus is this infinite straight. And so this problem has similarities at this infinite number of points. And when we divide by solution of the three-point problem, we cancel this singularity and monodromy around it, and we cancel monodromies around these two sides. So we get some function which is analytic in this parallelogram. And once we see this, it is a place where see that it is an Hilbert problem. And namely, so it was a sphere would have some function which is analytic in one domain, and we could also consider some other parameters which corresponds to the complementary domain and do the same procedure, and then we will need to compare these two functions between different domains and say that there is some jump condition. And here we have just one domain, but we should identify this A cycle with this A cycle. So the jump condition should be written for this side. And we actually do this. Since we have this explicit formula, we know how this y and y tilde are transformed. We can say that it is just periodic in one direction. And in the other direction, we should multiply by first by this non-trivial matrix describing a complex modulus of vector bundle, and second we should multiply by some jump matrix. And the jump matrix is given by the ratio of the solution of this three-point problem close to plus infinity and close to minus infinity. So it is this formula. So one thing to notice here is the following: that if the element Hilbert problem is on a sphere, then it is just some relation between functions. But in the current case, we should solve the same Hilbert problem in assumptions of vector bundle, and modules of this vector bundle should be adjusted according to the jump metric, but otherwise in this problem will not have solutions. So it's one different than spherical dimensional problems. So so here it was just about some way to find explicit find some approximation to the solution. So in principle it can be done iteratively when tau goes to infinity and the jump will be small, and we can find some series. Actually, it turns out that it's not only about the approximate solution, but also about the exact solution. And namely, we can directly take this jump matrix and construct some determinant from it. Before we did this little material in the spherical case, and here it was very simple. And there was a Fredholm constant which depended on some jump matrix. And we could just take this jump matrix from the Hilbert problem, and it turned out that it is an Isomonodromic function. Just combine two natural objects and got this result. And here it's a bit trickier because this Fredholm determinant should be written on a torus. So are the ingredients that appear. So here I wrote a solution of this three-point problem, but we only need to know that it exists and it can be written explicitly. And if you want to construct the tau function, we should consider the following detail, which is which has the following stuff. So each block here is some 2x2 matrix depending on Z. So it acts on and these blocks of matrix bigger blocks corresponds to positive and negative powers in Z on the functions on the side. So let's set positive and negative Fourier modes. So there is this determinant which consists of projection operators and the multiplication by this jump matrix, and also it contains this weight operator which measures the number of the Fourier mode. And this operator also contains some letter rho, which corresponds to additional U1 twist of bicycle monodromy or bicycle twist, because it does not matter whether we count it as a monodromy or as some additional modules to a complex bundle, because we cannot distinguish left and right applications. So there is this extra parameter, and if we compute this Fredholm determinant, it turns out that it has the following form. It is a product of some theta ones of rho minus, in our case, minus and plus q, times some function of star. So it's the only place where this rho enters, and the result of this formula is that if you want to find coordinates of a particle, we need to compute the Fredholm determinant and find its zeros in rho. And it's also similar to the form people present solutions of multi-particle dramos are the autonomous case. They also have some zeta function that depends on one letter. You need to find zero zeta function in that letter. Characters, and this how model is defined by the condition that its logarithmic derivative is so I see that here it's problem on a torus. There are different Pavlo functions which are natural in different situations. So this usual Pavlo function is natural because it is directly related to the Estonian. But this Pavlo function with extra theta ones is more natural because it has the determinant representation. It also has that explicit expressions in terms of recursive functions. And also, if you want to write to get this formulas in terms of recursive functions, we need to consider that minor expansion of the determinant. And it turns out that you can compute this maths explicitly, and this recursive factors are just the values of this minors. And this pair of invariants parameterizes which particular minor in the computed. If you want to recover the formulas for Q, which we had before, we can compare the raw dependence of the left-hand side and of the right-hand side. So there are formulas for the left-hand side for this determinant, which can be obtained as a result of this minor computation. And the answer is this. It is a product of theta 2 of rho multiplied by this series with epsilon equals to 0 plus theta 3 of rho multiplied by a series with shifted arguments. And then we can look at the right hand side and write this product of theta functions in a basis functions of rho. Just compare the coefficients in this expansions, the two terms, and then get formulas like this, and then just divide to get rid of the Pavlo function, which you don't want at the moment, and see that there is this equation, the ratio of theta functions equals to the ratio of such combinatorial series.
Epsilon is possible.
Zero.
Epsilon is either 0 or 1.
Yes. Yes. Thank you. It's epsilon over 2 here.
What is
Yes. So it should be just 1.
Oh, yes.
Yeah, actually, this formula is very close relative for the formula of the solution of Penrose 3, because we have a limit from here to Penrose 3. In that case, it just gives Penrose transcendent as a ratio of two Pavlo functions. But here, it's not just an arc consonant, it's a tau-dependent function of arc consonant. And Are there any questions about this?
Maybe about the previous part. You might want to understand that segment modular, which is this. So, if instead of considering regular singularity, we have the derivatives, so would it complicate this as well? Can one do Isomonodromic deformations on the torus for the irregulars?
I think yes, of course, because in principle, this different monodromy, which you call twist, is a modulus of retromotor. It appears only for the dissonant, and there is nothing around zero. So it is it is something that the theory in orbit element of our call. It is about the global behavior of solution. So maybe we can try to say it this way. And when we work with Raymond with some space functions on a sphere, and we want to divide it into two parts that don't intersect. We consider no, maybe. If you want a function that if you want to define some space of functions of dimension 0 on a sphere, we should say that they are homomorphic everywhere and they are also 0 in some point. In this case, it becomes 0-dimensional. On a torus, there are homomorphic functions, and the condition that kills this one-dimensional space is precisely this monodromy condition with so functions homomorphic and that have monodromy to find Q. And the role of this role which we have here is to shift both eigenvalues Q and minus by some role, and at the point where Q becomes when rho becomes Q or minus Q, we get for one-dimensional spaces instead of 0, because the homomorphic column vector becomes again an element of space. So that's why it's explanation.
But I mean, you could consider some linear system in which there is a decomposition first of rational functions on torus, and the rational function happens higher order.
Yes.
And then the case that you also need the functions that show up for the coefficients to be double periodic because of the torus.
The problem is that if we if we impose some condition that this Lorentz matrix is double periodic, we will just lose the possibility to perform isomonodromic deformations. Because here this Q evolves with time. If we don't allow this, we just will not have isomonodromic deformations. So, and on the Riemann-Hilbert problem side, it will mean that we cannot solve the same Riemann-Hilbert problem. Okay. So now about the modular properties of this problem. So if we just look at this equation, we can notice that there is a transformation of Q, which is originally we can write it as a transformation that represents the Vertas function. So we should multiply it by tau and take the argument minus 1 over. But it's actually a symmetry of equation itself. So you can have a derivative on tau, then become derivative on minus 1 over tau. But since Q is multiplied by tau, all the terms cancel. And in principle, such symmetry was also a symmetry of the linear system, because it was a system on a torus, and we could just rotate 90 degrees, scale z by tau, and it will effectively switch in the cycle monodromies inverting one of them. So, we can easily check that this solution is also a solution of the equation. And if we ask what are the precise initial conditions for these solutions, we can just read it from the monodromies. If we know these initial conditions, then we exchange this matrix with the inner one of them, and to find the mapping between these parameters, we just need to say that traces of this monodromies coincide for under the rotation. So, it is easy. And if you choose the appropriate variables, then these equations can even be solved. But it works not like we can express this two variables in terms of this. To do this, we will need to solve some quadratic equations. But if you, for example, try to choose these two variables, and a and eta tilde, then eta and a tilde can be expressed in terms of small tail. It is a little bit simpler than in the info point case. Easier to work here. So here it was about the economic consent. Now the question is, what happens with the tau function? So, in principle, tau function was defined only by its tau derivative. Also, even this tau derivative has problems, because this Q is multiplied by some tau, which means that momentum will be shifted, so Hamiltonian will be shifted, and all this leads to the fact that this single tau function is multiplied by Penelak constant square divided by tau exponent of this object. So it's first term which is unavoidable because of this transformation property. But also, since it was defined only as its Riemann derivative, it can and it will be multiplied by some function independent on tau, which is called connection constant for the tau function. And we can see this connection constant again in this trivial free particle case. So, as a monodromic tau function of the free particle is e to the 2 pi I a squared times tau, and the dual tau function. So this a is a momentum. But if you compute dual tau function, momentum and coordinate will be exchanged, and we should get e to the 2 pi I eta squared, now divided by tau, because it was mapped tau to minus. And this strange transformation between coordinate and momentum is achieved precisely by this non-trivial tau dependent. So this tau function behaves really strange. It is multiplied by function dependent on tau. But if you look at the other tau function, which is this Fredholm determinant, which contains theta functions. Then this tau-dependent prefactor is cancelled. That complicated prefactor that dependent on Q cancels, and it has just this multiplication by e to the pi r squared over tau. So this is easier. Now, another question: how to compute this connection cost? So, since the first problem where this connection constant was computed was for kernel 6, and it was first conjectured by Gavrylenko and then proved by its and here I will tell what happens with such approach in the toric case. So, what we need to do? Originally, we have the definition of this the tau function by its logarithmic derivative in tau. And to be able to study its monodromy dependence, to be able to capture this connection constant, we need to add some part which depends on monodromies. And this strategy to do this was proposed by Oleg, and it is the following. You just should take this Fredholm determinant, which we have, and compute its logarithmic return. It is doable, and the answer is the following. Logarithmic derivative of this, then we translate it to the formula of the logarithmic derivative of the tau function, and the answer is the following. It is this original term. It is this monodromy dependent piece which is absent in the spherical case. It is PDQ, but with monodromy only derivative. And there are such pieces related to the singularities. There is derivatives of matrices that diagonalize connection matrices in our problems. So, so we have this one form, and those get automatically another one form which is related to this auxiliary stepwise problem. So, and if you compute this one form, say in our one point case, we see that it is some one form written on a little bit extended space. Because we have this PDQ as usual, but we also have a variable which is conjugate to the residue at 0, and this variable is responsible for the diagonal part of the matrix, the diagonal left of the matrix. So we have one form of the extended space, and now we have different subpoint parts which appear in the original problem and in the dual one. And to compare the connection constant, we just need to compare this additional subpoint problem, this additional subpoint one forms. And if you just take this ratio and just integrate it, you will get explicitly a formula for this connection constant, which contains some trivial responsible for normalization of the tau functions. And it also has some explicit ratio of this ratios of Gauss functions, or it can be written in terms of little divergence. What is this one? So in the m equals to 0 case, the Telus is just with the Fourier transform, like pi a tilde, a tilde. So, there are minutes now. The difference between this formula and the formula in the footprint case that here it is just explicit in terms of monodromy data A and it appears that we don't need to solve any this connection constant. And also having this, we can get the transformation property of that conformal blocks, which appears in the formulas for them. Basically, we know what that we have two Fourier series for the tau function and for the dual tau function. And we know that modular transformation corresponds to multiplication by some function. So, and if you want to get transformation of this conformal blocks, we just take a single term of this series by considering such thing. And then we substitute that it equals to this the connection constant times another sum, compute that integral, and get the integral of this form with some matrix S. This integral is over the entire real line shifted by some imaginary number, or it can be reduced to the half line due to the same thing. And the kernel which appears here, which is called fusion matrix, is given by the connection constant times the cobarian of this transformation from eta tilde to a tilde. So, given this explicit expression, the same as in the sixth case, or so.
Question? So I have one question. So now you're taking this equation, the non-autonomous scalar and now tau is a complex time, but if you think of some real form of this equation, can you study whether it's not smooth, the real smooth solution? It's like that. Is there any geometrical meaning to that?
Of course, we can consider tau to be purely imaginary, and the initial conditions should be appropriate. So it will be some real equation, and we will have this rate of symptotic set at almost zero, and so infinity. By geometry.
No, I don't like when we I was thinking about finite gap solution of KDD, and then you study like hyperlaptic curves which are like M curves or not. This is like there are cases where solution of KDD, the real solution has moved or not, depending on some properties. Geometric properties.
Yeah, I can answer. So for me, the sterile case is important if you want to study some self-adjoint Schrödinger fields. So in that case, we have something which family of problems, because this classical problem corresponds to corresponding quantum problem with Weierstrass potential, and we can see it on the line shifted by tau over 2. In this case, potential will be real, and it will be periodic without singularities in this case. So we will be able to study this another option is to take a line from 0 to 1. In this case, potential is also real, but now it will have this numbers at the end, and it will correspond to the structural problems of Well, something similar to the unit AE, so it will be displayed back on. So this is the only application of potential and the final. There's also another real torus, which is equals and well, in that case we don't have this periodic potential, the conformal, but we still have potential of this spectrum going from 0 to tau plus. So this is the only application that I know where it is important to have some real structure.
It's mainly about can look at the application of line equations and check.
Probably, yes.
And the question was you can relate, for instance, modular transformation to some property of the 6 sphere.
Yes, it is more or less the same transformation.
So it's like what people call Schlesinger.
No. So transformation probably is about shifting meters by 18 to just here there should also be some transformation or effects on.
So the BS.
No. If we study the D transformation, it is just calculus 1, function will go over some identical number.
Any other question? If not, let us thank Pavlo again.